So, what if the world you see around you, the three dimensions you walk through every single day, what if that's just a tiny slice of a much, much bigger reality? That's the wild, mind-bending idea right at the heart of string theory. It suggests that our whole universe is built on things we literally can't even see.
You see, for the math in string theory to actually work and not just fall apart, our universe can't get by with just the dimensions we already know about. The equations demand a very specific number, 10. A full 10 dimensions of spacetime. That's 1 for time and 9 for space.
And right away, that leads to the obvious question, right? If there really are 6 other spatial dimensions out there, why can't we see them? Where in the world are they hiding? Well, that's the exact mystery we're going to try and solve today. Okay, so before we go hunting for these hidden dimensions, we really need to get on the same page about what a dimension even is. It's a word we all use, but in physics, it has a very, very precise meaning. So a dimension is basically just a degree of freedom. That's a fancy way of saying it's an independent direction you can move in or measure something. I mean, think about it. To tell someone where you are in a room, you need 3 pieces of info, right? How far forward, how far to the side, and how far up. Length, width, height. That's 3 dimensions. If that still feels a little abstract, here's another way to look at it. Think about a dating website. It's using dozens of dimensions to find you a match. You've got age, location, income, education. Each one of those is a degree of freedom that helps pinpoint a person in the, space of possible partners. It's the exact same idea, just applied to people instead of particles. And we can build up the dimensions we know and love pretty intuitively. Let's start with a single point. It has 0 dimensions. Now, stretch that point out, and boom, you've got a one-dimensional line. Stretch that line out at a right angle, and you get a 2-dimensional plane. Do it one more time, pulling that plane straight up, and you've got a 3-dimensional cube. Up, down, left, right, forward, back. Our world. All right, we've nailed down our 3 spatial dimensions, but modern physics tells us there's a 4th player in the game, and it's the one that we are all hurtling through right now. Time. Now, Einstein gets all the credit for this, but fun fact, it was actually his old teacher, Hermann Minkowski, who first put relativity into this elegant 4-dimensional space-time package. He's the one who realized that space and time aren't 2 different things. They're woven together into one single fabric. But, and this is a huge but, time is a different kind of dimension. You see, you can swap left for up in an equation, and the physics still works just fine. But you can't just swap left for tomorrow. The math itself keeps time separate from space. You can move any which way you want in space, but you are always moving forward in time. So that gets us to the 4 dimensions we're familiar with. But string theory says, nope, there are 6 more. Which brings us back to the main question. Why? I mean, what's the point of them? The answer, really, is all about the math. When physicists try to write the equations for string theory in just our normal 4 dimensions, the math just breaks. It goes haywire. It starts spitting out impossible answers, like the chance of something happening being negative. But then, almost like magic, when they add 6 more dimensions to the mix, for 10 in total, everything just clicks into place. The equations suddenly make perfect sense. Now, it's really important to get this part. This isn't some absolute law of the universe that's been proven. As this quote points out, doing string theory in 4 dimensions might not be impossible, it's just insanely complicated. So for most physicists, using 10 dimensions isn't so much a claim about reality as it is just taking the most elegant and straightforward path to get the math to work. Okay, so if the math needs these extra dimensions to exist, then where are they? The leading theory for how they could be hiding in plain sight has a fantastic name: compactification. Compactification is this idea that those 6 extra dimensions are all around us, at every single point in space. But they're curled up into a shape that's so unbelievably tiny, we're talking down at the Planck length, that we can't see them or interact with them at all. I know that sounds absolutely impossible to picture, but there is a perfect analogy that really makes it all click. Just imagine a simple garden hose. When you're looking at that hose from way across the yard, it just looks like a line, right? It's a one-dimensional object. As far as you're concerned, the only way to move is forward or backward along its length. It just has one big, obvious dimension. But if you were a tiny ant standing on that hose, you'd discover a whole new reality. You wouldn't just be able to walk along the length, you could also walk around the circular part. That second dimension was there the whole time. It was just compactified,
curled up so small we couldn't see it from far away. String theory basically says our universe is just like that, but with 6 hidden dimensions instead of just 1.
But what if that's all wrong? What if there aren't any extra dimensions curled up anywhere? Turns out some physicists are arguing for a totally different way to make the math work, one that doesn't force us to believe in a universe we can't see.
So you've basically got two camps. On one side, you have the standard 10-dimension approach. It says the extra dimensions are real, but tiny, because it makes the math work out beautifully. On the other side, you have the 4-dimension approach. It says those extra degrees of freedom the math needs aren't dimensions at all, but new, built-in properties of particles, things physicists call charges. The trade-off? The math gets way, way messier.
This whole thing creates a really fascinating puzzle. We often fall back on a principle called Occam's razor, which says the simplest explanation is usually the best one. But in this debate, the razor cuts both ways. It forces you to ask a really deep question about what simple even means.
And that's really the question at the bleeding edge of physics right now. What's truly simpler? A universe that has 10 dimensions, 6 of which we can never, ever see? Or a universe with just the 3 dimensions we know, but filled with a bunch of complex invisible properties that make everything work? The honest answer is, we just don't know yet.